Welcome back, class. In the next couple sections, we're going to look at various types of calculations where we are going to be calculating some or all of the equilibrium concentrations based on if we know the initial concentrations and, of course, the equilibrium constant. So we're going to start here with sort of the most straightforward type, what we call like a simple level calculation, where we know the initial concentrations and we also know one equilibrium concentration. Now, all of these types of calculations that we're going to look at are going to utilize what we call ICE tables. Now, we'll see that an ICE table stands for initial, change, and equilibrium. So we have our ICE table. And these will come pretty self-evident once we start using them. So let's look at our approach here. So let's take this example. So let's say we have the reaction of carbon monoxide, and 2 moles of hydrogen goes to 1 mole as an equilibrium with 1 mole of methanol. And we know our starting concentration, so in this case we start with our reactants. In this case we have 0.5 molar CO, 1 molar H2, and we don't have any product at the beginning. We know that at equilibrium our carbon monoxide has a concentration of 0.15. So the first step, right, is because we know the initial and the equilibrium, we can calculate the change, right? And we can see it clearly. It has gone down because we're reacting our reactants to make product. So if we do our calculation, we see that this goes down by 0.35. So our first step would be we generate this. Now, the key is once we know one of the changes, we can use the balanced equation to get the other changes by looking at the coefficients here. So if we know that CO went down by 0.35 and we know there is a 1 to 2 relationship, we know that H2 must go down by twice as much, or must go down by 0.7. And because of the 1 here, right, there's a 1 to 1 stoichiometry, so if this goes down by 0.35, this must go up by 0.35. So we're going to use stoichiometry to figure out the other changes. So that's our second step. Okay? Now, once we know the changes, then it's just a matter of doing our addition or subtraction to figure out what our final concentrations here. So if we take our 1 minus 0.7, we get 0.3. If we take 0 plus 0.35, we get 0.35. So we utilize our changes to figure out what our equilibrium concentrations are. So pretty straightforward here. Now, at this point, we could use these equilibrium. We could use these to find K. Okay. So I'm not going to worry about that here, but this is something that we'll be doing a lot of as we go through it. We'll be coming up with our equilibrium concentrations. And Some cases we'll use them to find K. Other times we'll be given K because we need the value of the equilibrium constant to figure out what the equilibrium concentrations are. Okay, so let's close out this particular section with one more example, and we'll use this equation here, where we have 2 moles of methane in equilibrium with C2H2, ethylene, and 3 moles of hydrogen. So we have the same kind of scenario here. We know our initial concentrations. In this case, we know that we start off with only CH4. And we also know the equilibrium concentration, in this case, of C2H2. So we go through the same approach. The first thing we do here is we calculate a change. In this case, it would be of C2H2, right? The one that we know both of. So we know this went from 0 to 0.035. So this went up by 0.035. Then we're going to use stoichiometry to figure out other changes. So in this case, there is a 1 to 2 relationship between the C2H2 and the CH4. So this change is going to be 2 times 0.035. Now, something to pay attention to is the signs here, right? Because in this case we started with reactants and we have no products, that means our reactant concentrations, while our product concentrations are going to go up, like we see here, our reactant concentrations are actually going to go down. So in this case, it's going to go down by 2 times. And so it's going to go down by 0.070. And we have a 1 to 3 relationship between the 2 products. So if this goes up by 0.035, this is going to go up by 3 times. And so this is going to go up by 0.105. And so now it's a matter of just doing the math. And so we take our 0.115 minus 0.07, we end up with 0.045 as our concentration here. Of course, if 0 plus this, we end up with 0.105 as my final concentration here. Okay. So, last step here is calculate equilibrium concentrations. All right, so that's a pretty straightforward type of problem. So this is, sort of the low, kind of a low level of difficulty. If we know the initial concentrations, and we know one of the equilibrium concentrations, we can do it based on stoichiometry. Now, in the next section, we're going to look at a little bit more advanced problem where we don't know any of the equilibrium concentrations. Welcome back, class. We've just spent time looking at how to solve an equilibrium problem if we are given at least one of the equilibrium concentrations along with the initial concentrations. But what if we aren't given any information about the equilibrium constants in the sense of we can't predict the change based on knowing both the initial and the equilibrium constant. And so, in order to work with these kinds of problems, where we may or may not know which direction the reaction has to move to get to equilibrium, because we don't have enough information, we need to have a tool that we can use in order to predict the direction that a reaction will proceed to get toward equilibrium. And that tool is something called the reaction quotient. And so, if we are starting with a reaction, specifically this is most useful if you have both reactants and products. Now, we'll apply this idea just to understand it as well in reactions where we start with just reactants or just products, and we'll see kind of how Q would help us understand that. But the idea is we're going to solve for the reaction quotient Q. Now, Q is just simply the equilibrium expression. So it is the same format as the equilibrium constant, meaning we have the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. The key is we are not at equilibrium, right? This is a non-equilibrium condition ratio. Now, by doing this and we get a value for Q, we can then compare that value of Q to what the rate constant is, and we can then determine whether Q has to get smaller to match up with the equilibrium constant, or if Q has to get bigger to match up with the equilibrium constant. And by understanding that, we'll know whether products, the top of our ratio, has to get bigger or smaller, or whether reactants have to get bigger or smaller, right? So we can tell by if Q needs to get smaller or larger, whether reactants are increasing or products are increasing. Now, the two extreme conditions that I mentioned was if we do just start with reactants, so we only have a value on the top here, and of course the bottom would then be 0 if we don't, the top would be 0 if we don't have any if we don't have any products, and so we have 0 on top, whatever the value from our reactants on the bottom, and of course Q then will be equal to 0. And the reaction will proceed toward products because K, the equilibrium constant, won't be 0. Now, on the other hand, if we have only products, then we're going to have a value on the top, but 0 on the bottom, so we're going to get division by 0, and in that case, our ratio would be infinity, and we get in that scenario, we would know that the reaction is going to go toward reactants because we need to get a value for K, right, that's not infinity. Right? So at equilibrium, there's going to be at least some of both the reactants and products. So of course, those are the two sort of extreme conditions. Most of, we'll look at problems like that just to kind of get used to it. And then you'll also see problems where you have some of both and you really do have to use Q to predict the direction. So let's look a little bit more at Q. So remember, Q or K, right? It's always products over reactants here. So if we compare it, right, if Q is big, right, so if we solve for Q and we get a value larger than K, well, what does that tell me? We need to get this ratio to be smaller. And the only way to get that ratio to be smaller is if we lower the products and raise the reactants, right? So to make our ratio smaller, we need to make the products smaller, the reactants larger, and that means the reaction has to move to the left. So in order to drop the value of Q down so it matches K, so the reactant's going to proceed toward the left. Now, in the opposite scenario, if Q is less than K, then the reaction will proceed toward the products because we need to make Q bigger in order to match K. And the way we make Q bigger is to make the top, the products, bigger, the bottom, the reactant, smaller. That's going to make our ratio larger, and it's going to move Q toward K. So the reactant's going to proceed to the right. And of course, if you solve for Q and it equals K, it just means you were already at equilibrium. And so that's what this diagram is showing here. So this is at your equilibrium constant. So if you are over here to the right on our diagram, that means we have more products than we should at equilibrium. So we're going to move this direction. So the products are going to get smaller, reactants are going to get bigger. If we're down here and Q is smaller than K, we're going to move in this direction, causing products to increase, reactants to decrease, to raise up Q to match K. So that's the idea of the reaction quotient. Now, we're going to now look at some types of problems where we're going to maybe utilize that. But before we get to one where we're actually going to utilize Q, the general type of problem we're going to be solving is solve problems to find the equilibrium concentrations when we don't know anything really. We can't do it stoichiometrically, put it that way. So one type of simple problem, and this is by far the simplest type of problem, is if we don't know anything about the initial situation, but we know the equilibrium constant and we know all but one of the equilibrium concentrations. Now, if we're in that scenario, of course, we don't need to know anything about the equilibrium because we can simply plug and solve. So if we take this example where I2 is in equilibrium with 2I, so the equation for K here is going to be products, so the concentration of I squared, over reactants, the concentration of I2 raised to the first power. Now, if we plug in what we know that the concentration of I2 is 0.1, so we have I squared over 0.1, and now it's just a matter of simple solving, and we get I squared equals 0.011 times 0.1, or 0.0011. And so if we take the square root of both sides, we get the concentration of I equals the square root of 0.0011, which equals 0.033. So this is the simplest type of problem. Now, in the next section, we're going to look at problems where we have to go back and start using our ice tables again. So we're going to know something about the equilibrium constant and the initial concentrations, but we're not going to know anything about the equilibrium concentrations. So that's what we'll start off in the next video.